It was a Monday morning, which is already a hard sell for most of us, and across the southern Philippines, it was the first day of school. Kids in fresh uniforms, the ones that are always slightly too big because you buy them to last the year. Parents doing the usual shuffle of bags and shoes, and one last reminder about something. The kind of morning that doesn't get written down anywhere, because nothing about it is meant to be remembered. And then, at 37 minutes past 7, the ground had other ideas. That's where we're starting tonight. But I want to be upfront with you about something before we go any further, because I think it sets the right mood for the next couple of hours. This isn't a news broadcast. I'm not here to frighten you about what's coming, partly because I'd be a hypocrite, given that the whole point of this channel is helping you switch your brain off and go to sleep. So if you came expecting sirens and dramatic music and a man with a serious voice telling you the end is nigh, I'm afraid you've got the wrong video, and I'd gently point you elsewhere. What this actually is a long, slow wander through one of the most genuinely fascinating subjects I know of. Why the Pacific shakes the way it does, what we understand about it, which is a surprising amount, and what we don't understand, which is, honestly, more than you'd think, and in a way that I find oddly comforting rather than scary. There's a line in the title there, the bit about the worst still being to come. I'll be straight with you, because we're going to be spending the evening together, and I'd rather not start on a fib. No seismologist on Earth can tell you when the next big one is going to hit. That's not me being coy. We'll get into exactly why later, and it's one of my favourite parts. But there is a sense in which the worst is in fact always still to come, and it's a sense that has nothing to do with prophecy and everything to do with very slow, very patient geology. It's a bit like knowing that one day it'll rain again. You don't know the day, you just know it's coming, because that's what the sky does. The ground under the Pacific is a bit like that. We'll come round to it, no rush. For now, all you need to do is get comfortable. Sort your pillows out. If you're the sort of person who falls asleep 20 minutes in, that's completely fine. That's rather the idea, and you won't miss anything important, because I've built this so that there isn't really an important bit. Every part sits alongside the others. You can drift off during the giant earthquakes of the 1960s and wake up somewhere near the bit about why tsunamis behave so strangely, and you'll have lost nothing but a few minutes of me nattering on. If you do happen to enjoy this sort of thing, and you fancy more of it, a quiet subscribe does help the channel along, and I'd be grateful. That's the only time I'll mention it. I find it a bit much when people beg at the end, when you're meant to be falling asleep. Right, the earthquake itself. On the 8th of June 2026, a major earthquake struck just off the coast of the southern Philippines, near the province of Sarangani, on the big southern island of Mindanao. It measured a magnitude 7.8, which is a serious number, and we'll talk later about what that number actually means, because it's not what most people assume. It happened offshore, out under the water, which matters a great deal for reasons we'll come to. A tsunami warning went out across the region. People moved to higher ground, and then a few hours later, the warning was stood down, the waves having turned out to be far smaller than the worst-case fear. That, in the broadest strokes, is the event. People died, which is the part you can't ever quite tuck away neatly, and I won't pretend otherwise. But the place it happened is a place that has shaken many times before, over many generations, and has rebuilt many times before, and there's something quietly steadying in that when you sit with it long enough. So that's the plan for tonight. We'll start close with what happened that morning. Then we'll pull back, further and further, until we're looking at the whole Pacific and the slow machinery underneath it. We'll visit some of the largest earthquakes ever recorded, which are honestly some of the most astonishing events in the planet's history. We'll do a proper detective story involving a wave that turned up in Japan in the year 1700 with no earthquake attached to it, which is one of the best things I've ever read about. And we'll end up, eventually, back at that quiet question of what's coming, and why not knowing is, I'd argue, exactly as it should be. Settle in. We've got a while. Let's stay with that morning for a little while, because the details of it are worth knowing properly before we go wandering off into the bigger picture. The earthquake's epicenter, which is just the spot on the surface directly above where the rupture began, was offshore, roughly 32 kilometers west of a town called Marsim in Sarangani. So it didn't happen under a city. It happened out at sea, with the actual break occurring about 33 kilometers down into the earth. That depth is going to matter to us later, because where a quake happens, both sideways and downwards, shapes nearly everything about how it's felt. For now, just file it away. 30-odd kilometers down, a fair way offshore, early on a Monday. The shaking reached a good chunk of Mindanao. There were reports of people who could barely stay on their feet, of the ground moving in a way that makes you grab for a door frame before your brain has even finished deciding to. Some buildings came down, not many in the grand scheme, but enough. And in the way these things go, it tends to be the older or the weaker structures that suffer first. A few smaller buildings collapsed or were badly damaged, and that's where most of the harm happened. Now, because it struck offshore, the immediate worry wasn't only the shaking, it was the water. The Philippine Seismology Agency, which goes by PHIVOLCS, put out a tsunami warning for a long list of coastal provinces, and people did the sensible thing and moved inland and uphill. This is one of those moments where I have a lot of respect for how routine the response has become in that part of the world. Living on a coastline that shakes teaches you things, and it teaches them down the generations. Here's the bit I find genuinely reassuring though. The waves that actually arrived were small. We're talking roughly a metre at the nearest coasts, with less than that recorded further along. A metre of tsunami is not nothing, and I don't want to wave it away, but it is a very long way from the towering walls of water that the word tsunami tends to summon in the imagination. And within a few hours the warning was lifted entirely, because the threat had genuinely passed. The system did exactly what it's built to do. It rang the bell loudly, just in case, and then it had the good sense to go quiet again when the danger didn't materialise. We'll talk later about why being able to stand a warning down is just as clever as being able to raise one. The other thing worth sitting with is that this region is no stranger to any of this. According to the historical records, at least 7 significant earthquakes, ranging from around magnitude 5.7 up to magnitude 8, have affected Sarangani and its neighbouring provinces between 1917 and 2023. The most recent damaging one before this was a magnitude 6.8 back in November of 2023. So this is not a quiet patch of the planet that suddenly turned on its inhabitants. It's a part of the world that has been having this conversation with the ground for as long as anyone has been keeping notes, and almost certainly far longer than that. I think that context does something useful to the feeling of an event like this. A single earthquake, viewed on its own, feels like a catastrophe that came out of nowhere. The same earthquake, viewed as one entry in a list that stretches back over a century, feels more like weather. Severe weather, the kind you prepare for and respect, but weather all the same. Part of the deal of living where these people live. Sort of like how folk who grow up somewhere with proper winters just know, in their bones, how to drive on ice, while the rest of us go sliding into a hedge at the first frost. A small detail that stuck with me, and I'll mention it because it's the sort of thing that makes a statistic feel like a real day. The quake hit on the first morning of the school year. Across the region, that meant a lot of children gathered in courtyards and classrooms when the ground started to move. In one school, kids were said to have swayed where they stood as the shaking came through and a metal awning gave way above them. Everyone in that particular yard was all right, as it happens, but there's something about the image of it, the brand new uniforms and the swaying, that I haven't quite been able to put down. There's one more piece of housekeeping before we widen the lens, and it's about that depth figure I asked you to file away. 33 kilometers down is what seismologists would call a shallow to moderate depth. Shallow quakes, the ones nearer the surface, tend to shake the ground above them harder, because there's less rock in between to soak up the energy. Deeper quakes, the ones happening 100 or 200 kilometers down, can be felt across enormous areas, but often do less violent damage at any one spot. This one sat in that middle ground, close enough to be felt strongly across Mindanao, far enough offshore that the worst of it spent itself on the seabed and the open water rather than directly under anyone's home. And that's really the shape of the 8th of June. A serious quake handled by a region that knew the drill, with a tsunami that thankfully stayed modest and a warning system that did its job and then politely got out of the way. Now, to understand why any of this happens at all, we need to go down. Not metaphorically, actually down into the rock to have a look at what an earthquake even is, because I think a lot of the fear around them comes from them feeling like a kind of punishment from below, sudden and meaningless, when really they're one of the most logical things the planet does. Picture a door that's swollen shut. You know the one. There's always one in every house, usually the bathroom or a back bedroom, that's taken on a bit of damp and decided it's no longer interested in opening smoothly. You push, nothing. You push harder, still nothing. The frame and the door are gripping each other, holding firm against everything you've got. And then, all at once, it gives, and you nearly end up on the floor of the room, because all that force you'd built up releases in an instant. That, more or less, is an earthquake. And I love that comparison, because it takes something that feels apocalyptic and makes it household. The outer shell of the earth, the part we live on, isn't one solid piece. It's broken into enormous slabs called tectonic plates, and these plates are slowly, ceaselessly moving. Not quickly. We're talking a few centimetres a year, about the speed your fingernails grow, which is a fact that gets quoted so often it's practically law, but it's quoted because it's a good way to grasp it. The whole restless surface of the planet rearranging itself at the pace of a fingernail. Where two of these plates meet, things get interesting. Sometimes they slide past one another. Sometimes they pull apart. And sometimes, in the cases we care most about tonight, one plate dives down underneath another, sinking back into the hot interior of the planet. That last one has a name worth knowing, because it's going to come up a lot. It's called subduction, from the same root as duck under, which is exactly what one slab of the planet is doing to another. One ducks below, the other rides over the top. Here's the thing, though. These plates don't glide along like well-oiled machinery. The edges are rough. They catch. They lock together and hold, gripping each other, exactly like that swollen door, while the deeper forces keep right on pushing. The strain builds and builds, sometimes for decades, sometimes for centuries, with nothing visible happening at the surface at all. The fault, which is just the name for the boundary where the rock can break, stays stuck and silent the whole time. And this is the part that explains so much about why earthquakes feel the way they do. Most of them strike without any warning whatsoever, because right up until the moment of rupture, there's nothing to see. The fault is locked, it's stationary. All that stored up strain is invisible. And then the grip finally fails, the rock snaps past itself in a matter of seconds, and all that energy, patiently accumulated over a human lifetime or longer, comes out at once as the shaking we feel. Seismologists have spent a very long time looking for some reliable signal that comes just before that snap, some twitch or hum or change in the rock that would let us know it's about to go. So far, they haven't found one. We'll dig into what that means for prediction later on, because it's central to the whole story. But I want to dwell for a second on what that actually tells you, because I think it reframes the whole thing rather beautifully. The energy in an earthquake isn't created in the moment it strikes. It was already there. It had been gathering for years. The quake isn't the planet suddenly deciding to lash out. It's the planet finally letting go of something it had been holding. The violence is in the release, not in the building, and the building had been happening quietly the entire time, under everyone's feet, while life carried on above completely unaware. The point where the rock first breaks, down inside the earth, is called the focus, or the hypocenter, if you want to sound clever at a dinner party, which I can't promise will make you popular. The spot on the surface directly above it is the epicenter, which is the word you'll hear on the news. And the depth of that focus, which is the figure I made you file away earlier, decides a lot. A break that happens near the surface delivers its energy to the ground, above hard and concentrated, like a punch landed up close. A break that happens far down has all that intervening rock to travel through, which spreads the energy out and softens its arrival, so it can be felt over a huge area while doing less damage at any single spot. Then there's the matter of water, which we'll properly unpack later, but which deserves a first mention here. If a fault ruptures under the seabed, and that rupture shoves the ocean floor upwards, or drops it down, then it doesn't just shake the rock, it shoves the entire column of water sitting on top of it. And water, being water, has to go somewhere. That's the seed of a tsunami, right there. And it's the reason an offshore quake carries a whole second category of risk that an inland one simply doesn't. The 8th of June was offshore, which is why the water was the immediate worry. A quake of the same size directly under a city would be a different kind of disaster, with different dangers and no tsunami at all. So that's the machine, in its simplest form. Plates moving at the speed of fingernails, edges that catch and lock, strain gathering silently, sometimes for centuries, and then a release, sudden and total, sending energy out through the rock, and, if it happens at sea, through the water as well. Not a punishment, not a mystery, just a swollen door, finally giving way. Now that we've got the mechanism, let's go and find the single most active place on the planet for all of this to happen. Because it turns out the Earth doesn't spread its earthquakes evenly. It plays favourites, and its overwhelming favourite is the Great Ring around the Pacific. Imagine you could lift up and look down at the Pacific Ocean from directly above, the whole vast thing, the biggest single feature on the surface of our planet. And imagine you could draw a line tracing every place around its edge where the ground is restless. You'd end up with a rough horseshoe, an enormous loop running up the western coast of South America, on up through Central America and Mexico, along California and up to Alaska, then bending back across to Russia, down through Japan, past the Philippines, and on into Indonesia and the islands of the South Pacific. A ring, more or less, drawn around the entire ocean. That's the Ring of Fire, and it is, without much competition, the most geologically dramatic place on Earth. The numbers attached to it are the sort that sound made up. Around 90% of the world's earthquakes happen along this ring. Not most of them, nearly all of them. And more than 450 million people live within its various zones, which is a population larger than the whole of Europe west of Russia, going about their daily lives on the most active stretch of crust on the planet. When you put those two facts next to each other, you start to understand why a video like this one even exists. The name, by the way, comes from the volcanoes rather than the earthquakes, though the two travel together. The ring is studded with hundreds of active volcanoes, the great majority of the world's total, and that's no coincidence, because the same subduction that causes the quakes also melts rock deep down and sends it up to the surface. Earthquakes and volcanoes are siblings, born from the same process, which is why you so rarely find one region without the other. I've got a soft spot for the volcanoes, actually, and I'll likely do a whole separate video on them at some point, because the stories there are extraordinary in their own right. But tonight they're supporting cast. What I find genuinely lovely about the Ring of Fire is how it stitches together places that otherwise have nothing in common. Think about it. Chile and Japan and Alaska and the Philippines and New Zealand and Indonesia. Wildly different languages, different climates, different histories, different food, different everything. And yet they all share this one strange inheritance. They all live on a floor that won't sit still. A fisherman in southern Chile and a schoolteacher in northern Japan have, underneath them, fundamentally the same problem, written in the same geological grammar, even if neither will ever meet the other, or speak a word of the same language. And the reason for all of it, the reason the Pacific specifically gets to be the headline act, comes back to that word from earlier: subduction. The Pacific is, in a sense, a closing ocean. Around almost its entire rim, the seafloor is diving down beneath the surrounding continents and island chains. That's an unusual arrangement. Most of the world's edges aren't doing anything nearly so energetic, but the Pacific is ringed, nearly all the way round, by these zones where one plate is endlessly sliding under another, and every one of those zones is a factory for the exact stuck and release process we talked about a moment ago. Multiply that process across thousands of kilometers of coastline, keep it running for millions of years, and you get the ring. There's a tendency, I think, to imagine the Ring of Fire as a sort of danger zone, a place marked with a skull on the map, somewhere sensible people would avoid. But that's not how any of this works, and it's worth saying plainly, so it doesn't sit in the back of your mind. These are some of the most beautiful, fertile, desirable places on the planet. Volcanic soil is famously rich, which is why people have farmed the slopes of dangerous mountains for thousands of years and judged it well worth the risk. The same forces that make the ground shake also build the islands, raise the mountains, and lay down the soil. You don't get the one without the other. The people of the Pacific Rim aren't living somewhere broken. They're living somewhere alive, and a living planet is, occasionally, an inconvenient one. I should mention the scale of the loop, because it's easy to lose. We're not talking about a tidy circle you could drive around in an afternoon. The Ring of Fire is something like 40,000 kilometers long, which means if you somehow stretched it out into a straight line, it would wrap right around the entire planet with plenty to spare. The earthquake off Sarangani in June was a single flicker on one small section of one arm of it. At that very same moment, somewhere else along the ring, the ground was almost certainly moving too, in some quiet way, too small for anyone to feel, because on a loop that size, at that level of activity, the stillness is never total. Somewhere on the ring, always, something is shifting. Now that brings up a natural question, and it's the one we're heading towards next. If this is the most active region on Earth, then it's also where the very biggest earthquakes happen. The true giants, the ones that don't just rattle a region, but reshape coastlines and send waves clean across the ocean. So let's go and meet a few of them, because they are, genuinely, among the most staggering events the planet has ever produced. And there's a thread running between the largest one ever recorded and that very same Philippine coast we started on tonight. 9.5. That's the number to sit with for a moment. The largest earthquake ever recorded by instruments struck southern Chile on the 22nd of May 1960, and it measured a magnitude 9.5. We're going to do a whole section later on, what these numbers actually mean, because the scale is sneaky, and most people read it wrong. But for now, just take it on faith that a number like that is, in energy terms, an almost incomprehensible event. The ground in Chile moved for minutes, not seconds, minutes which, when you're standing in it, must feel like the world has simply decided to stop being solid. What strikes me about the true giants is that they share a family resemblance. Every single one of the largest earthquakes ever recorded happened in the same kind of place, doing the same kind of thing. They were all what's called megathrust events, which is the technical name for a rupture along one of those subduction zones, where one plate is diving beneath another. When that enormous, locked interface finally lets go, and lets go along a vast length of itself, you get the biggest releases of energy the planet is capable of producing. Run down the list and the pattern is impossible to miss. Chile in 1960, the one we just met. Alaska on Good Friday of 1964, a magnitude 9.2, which shook the ground near Anchorage for the better part of 5 minutes, and is the second largest ever measured. Sumatra in 2004, a 9.1, the one that produced the catastrophic Indian Ocean tsunami. Japan in 2011, a 9.0, the Tohoku quake, which most of us remember from the news footage even now, and Chile again in 2010, a magnitude 8.8. 5 events, 5 of the most powerful things that have happened in modern history, and every one of them a megathrust on a subduction zone around the rim of the Pacific or its immediate neighbour. It is the same machine we've been discussing all night, simply running at its absolute maximum. The reason these particular faults can produce such monsters, while others can't, is down to size, and it's a point I'll come back to properly later, so I'll keep it brief here. The bigger the area of rock that breaks in one go, the bigger the quake. Subduction zones offer up enormous, broad, gently sloping surfaces that can rupture along hundreds, even 1,000 or more kilometers at once. No other kind of fault gives you that much real estate to break in a single event. So the giants live, almost exclusively, on the subducting edges of the Pacific. Now here's the thread I promised you, and it's the reason I wanted to tell you about Chile specifically, rather than just listing the big ones and moving on. When that 1960 Chilean earthquake ruptured, it didn't just devastate Chile, though it certainly did that. It shoved a colossal volume of seawater, and that water set off across the open Pacific as a tsunami. And because the Pacific is, for a wave like that, essentially a single connected body of water, the tsunami didn't stay home. It travelled. It crossed thousands of kilometres of open ocean, and roughly 15 hours later, it slammed into Hawaii, where it killed 61 people. It kept going. About a day after the quake, it reached the coast of Japan, on the far side of the entire ocean, and killed 138 people there. And it reached the Philippines too, where it took 32 lives. I find that almost unbearably poignant, and here's why. An earthquake in Chile, on one arm of the ring, reached out across the widest ocean on the planet and touched the very same Philippine coastline we began this evening talking about. The water connects them. A rupture on one side of the Pacific is, in the most literal sense, felt on the other. The ring isn't a metaphor or a tidy way of organising a map. It's a single system, and the ocean in the middle of it is the thing that carries the message from one edge to the next, whether anyone on the receiving end asks to hear it or not. That's also, if I'm honest, the moment I personally stopped thinking about earthquakes as local events. Before I understood the Trans-Pacific tsunami business, I had them filed in my head as things that happened to a place. A Chilean earthquake, a Japanese earthquake, as if each belonged to its own country. But the giants don't really respect those lines. They belong to the whole ocean, and anyone living anywhere on that vast loop is, in a quiet and usually harmless way, downstream of everyone else on it. I don't want to overstate the danger of this because most of the time these crossings amount to very little. The waves spread out and lose energy over such immense distances that, by the time they arrive far away, they're often small. The June quake's own tsunami, as we said, stayed modest, even close to home. But every so often, when one of the true giants lets go, the whole ocean basin gets the news, and the coastlines on the far rim get a few hours' notice to do something about it, which is precisely why a warning network that spans the entire Pacific exists, and why it's one of the quietly brilliant bits of international cooperation that almost nobody thinks about. We'll get to that. Before we get to the warning network, though, I want to dwell a little longer on just how big the giants really are, because there's a category of fact about them that I don't think gets nearly enough airtime. They don't only wreck coastlines, they physically alter the planet. And then I want to introduce you to a few faults by name, because some of them have become characters in their own right. After that, a quick word on the volcanoes, since they're family. And then I promise the detective story. Here is something that genuinely stopped me in my tracks the first time I read it. When the very largest earthquakes happen, they don't just shake a region and pass. They leave the entire planet measurably different afterwards, not poetically different. Different in ways you can put a number to with instruments. Take the 2011 Japan earthquake, the one most of us watched unfold on the news. When that megathrust let go, it didn't merely rattle the coast, it dragged a huge section of Japan bodily eastward. The main island shifted by something on the order of a couple of meters, permanently, in the space of a few minutes. Land that had sat in one spot for the whole of recorded human history, simply relocated, sideways, by more than the height of a person, and stayed there. Coastlines dropped. Harbours that had been above the water found themselves below it. The map had to be redrawn in the most literal sense, because the ground had moved out from under the old one. And it went further than that, out past the planet's surface entirely. A rupture that enormous redistributes a colossal amount of the Earth's mass all at once, and when you shift that much mass around, you nudge the way the whole planet spins. The 2011 quake very slightly altered the distribution of the Earth's weight, which in turn tweaked its rotation, shortening the length of the day by a tiny fraction. We're talking microseconds, millionths of a second, far too small for any human to ever notice. But it's real, and it's measurable, and I find it almost dizzying to sit with. An earthquake on one coast of one country reached up and changed how fast the entire planet turns. The day got shorter, not noticeably, but it did. This isn't unique to Japan either. The great Chilean quakes did much the same sort of thing, shifting mass, nudging the planet's axis by a small amount, shaving those imperceptible slivers off the day. It seems to be a signature of the true giants. Cross a certain threshold of size and you stop being a regional event and start being a planetary one, leaving fingerprints on the rotation of the world itself. There's a related effect that's easier to picture, and it happened all around the Pacific in the giant quakes. When one of these megathrusts releases, the land near it doesn't just shake, it lifts and drops. Whole stretches of coastline can rise up out of the sea or sink down into it in a single event. After the 1964 Alaska quake, the second largest ever measured, some areas were thrust upward by several meters, while others dropped, in places badly enough to drown coastal forests and sink docks below the tide line. Imagine the seabed near the shore suddenly heaved up into the air, dripping, exposing creatures that had spent their whole lives underwater. Or the opposite, a familiar bit of coast quietly going under, never to come back. The shape of the land, the thing we treat as the very definition of permanence, turns out to be negotiable on the right day. I think this is the fact that most rearranges how people feel about the ground. We build our whole sense of safety on the idea that the land is the one thing that stays put. The sea moves, the weather moves, but the land is the land. And mostly, on the human timescale, that's a perfectly fair assumption. But the giants reveal it for the convenient fiction it is. On a long enough view, the land is just slow water. It rises and falls and drifts, only at a pace we're usually too short-lived to perceive. The big quakes are the rare moments when that slow motion speeds up enough for a single human being to witness it happening, to actually stand there and watch the permanent turn out not to be. I don't say any of that to unsettle you. Quite the opposite, oddly. There's a strange calm in accepting that the ground is part of a moving system rather than a fixed stage we happen to perform on. It puts our worries in proportion. A planet that can shorten its own day with an earthquake is not a planet that's especially bothered about us. And there's a freedom in that. The same freedom you feel looking up at a clear night sky and realizing how much is going on that has nothing to do with you at all. Right, from the planet as a whole, let's zoom back into some specific lines in the rock, because a few of them have become surprisingly famous. Most faults are anonymous. There are countless thousands of them lacing the crust of the Earth, and the overwhelming majority will never get so much as a mention outside a specialist's map. But a handful have crossed over into something like public fame. They've got names people recognise, reputations, even a sort of personality in the popular imagination. And I think it's worth meeting a few of them properly, the way you'd want to know the regulars in a place you were going to be spending time. The most famous of the lot is almost certainly the San Andreas, running for hundreds of miles through California. It's the one that turns up in disaster films, the one with the blockbuster named after it. And it's a slightly different beast from the subduction monsters we've been discussing, because it's one of those faults where two plates grind past each other sideways rather than one diving under the other. We touched earlier on why that kind of fault can't produce the absolute largest quakes, so I won't go over the reasoning again. But the short version is that the San Andreas, for all its fame, is not where you'd look for a record breaker. What makes it loom so large in the public mind isn't its maximum size, it's that it runs straight through one of the most populous, most filmed, most written about regions on Earth. A fairly ordinary fault, by global standards, that happens to live next door to Hollywood. Then there's Cascadia, which we've already met in passing off the coast of the Pacific Northwest. This one is the genuine giant of North America, the megathrust capable of producing a true monster, the source of our orphan wave from 1700. And in recent years it's acquired a real cultural weight, a sort of looming presence in the regional imagination, often referred to simply as the really big one. There was a famous magazine article some years back that captured the public mood about it perfectly. And ever since, Cascadia has carried this aura of an enormous reckoning quietly waiting offshore. The phrase that gets repeated about it by scientists and locals alike is that it's not a question of if, but of when. Which is true. It's also, as we've established, completely silent on the actual when, and I gently fold the Cascadia anxiety into everything we said earlier about forecasting versus the calendar. The certainty is real. The date is not on offer, both things at once. On the far side of the ocean, Japan watches a fault zone of its own, with similar care, the Nankai Trough running along its southern coast. Japan has been living attentively with its ground for longer and more methodically than almost anyone, and the Nankai Zone has a long documented history of producing great quakes on a rough recurrence, sometimes in pairs, one section letting go and then another nearby following within days or years. The Japanese have studied it so closely and recorded its past behaviour so diligently that it's become one of the most carefully watched stretches of seabed on the planet, which is exactly the right response to a fault like that. You can't stop it, so instead you learn its history in such detail that you're as ready as it's possible to be. What I find quietly fascinating about these named faults is the way they take on a life in the local culture, almost like a difficult neighbour everyone has opinions about. People who live near them develop a relationship with them, a mixture of wariness, fatalism, dark practicality, and a strange sort of pride. There's gallows humour about the San Andreas in California, careful and constant preparation around Nankai in Japan, a low background hum of awareness about Cascadia in the Pacific Northwest. The fault becomes part of the identity of the place, not the whole of it by any means, but a thread running through it, a shared thing that everyone there carries, whether they think about it daily or have simply absorbed it into the furniture of life. And here's the thing I keep coming back to. None of these famous faults is behaving unusually. They're all just doing the ordinary work of faults, the locking and the loading and the eventual letting go, exactly like the thousands of anonymous ones we never name. The only difference is that these few happen to sit beside large numbers of people who write things down and make films and worry out loud. Fame for a fault is purely a matter of postcode. The ground itself is indifferent to whether it's famous. It just keeps doing what it does, under the celebrated faults and the nameless ones alike. Now, before we get to that detective story, I owe the volcanoes at least a brief visit, because they've been hovering at the edge of this whole conversation, and a couple of their stories are too good to leave out entirely. We've talked a lot about the shaking, and barely at all about the fire, despite it being right there, in the name of the ring. So let me give the volcanoes a proper, if quick look, because they really are the earthquake's siblings, born from the very same subduction, and a few of them have stories that I think about more often than is probably healthy. I'll save the full treatment for another night, since they deserve their own video, but a taster feels only fair. The one that haunts me most is Tambora in Indonesia, which erupted in 1815. It was, by most reckonings, the largest volcanic eruption in recorded history, And the truly remarkable thing about it isn't the eruption itself, but what it did to the rest of the world afterwards. Tambora flung such an enormous quantity of material high into the upper atmosphere that it spread around the entire globe and dimmed the sun. Not dramatically, not so you'd point at the sky and gasp, but enough. Enough to cool the whole planet by a noticeable amount for the following year or so. And that cooling had consequences that reached into places that had never heard of the mountain and never would. The year after the eruption, 1816, became known across Europe and North America as the year without a summer. Crops failed in the unexpected cold. There were frosts in months that had no business having frosts. Snow falling in early summer in places that should have been warm. Harvests collapsed, and with them came hunger in regions thousands of miles from the volcano, caused by a mountain on the far side of the world that almost none of the sufferers could have located on a map. One eruption on one Indonesian island quietly reached out and chilled 3 continents. There's a lovely cultural footnote to it too, and it's the kind of thing I find genuinely delightful. That cold, gloomy, sunless summer of 1816 trapped a group of writers indoors on holiday by a Swiss lake with nothing much to do but entertain themselves. To pass the dreary days, they challenged one another to write frightening stories, and out of that miserable, volcano-darkened summer came Frankenstein, a monster of English literature, born more or less directly from the weather caused by an eruption half a world away. I love that the ring's reach extends all the way into the books on our shelves. Tambora isn't the only one with a story like that. There was Krakatoa, also in Indonesia, later in the same century, whose eruption produced what's often described as the loudest sound in recorded history, heard across an almost unbelievable distance, thousands of miles from the mountain. People far away reported hearing what they took to be distant gunfire or cannon, with no idea they were hearing a volcano on the other side of an ocean. And closer to where we began tonight, there was Pinatubo in the Philippines, in 1991, one of the largest eruptions of the 20th century, which also threw enough material skyward to nudge global temperatures down for a couple of years afterward. The same country we started in, on the same restless ring, holds one of the great eruptions of modern times alongside its earthquakes. What ties all of this together, and what I want to leave you with before we finally get to the detective story, is that the fire and the shaking are one phenomenon wearing 2 faces. The same diving plates that lock and load and release as earthquakes also melt deep rock and send it climbing to the surface as volcanoes. You genuinely cannot have the ring of earthquakes without the ring of fire, because they are the same ring, the same process, simply expressing itself in 2 different ways. The ground that shakes is also the ground that occasionally opens and glows. 2 faces, 1 planet, both of them just consequences of a world that hasn't cooled into stillness and, thankfully for everything that lives on it, isn't about to. Right. Enough hovering. I promised you my favourite earthquake of all, and it's time I delivered. And I realise having a favourite earthquake is an odd thing to admit to, but this one is a proper detective story. It happened over 300 years ago, and we only worked out the full truth of it relatively recently, by piecing together clues from opposite sides of the ocean. Get comfortable. This one's a treat. Here's the puzzle, laid out the way it actually presented itself, which is the best way to enjoy it. In late January of the year 1700, a tsunami struck the coast of Japan. We know this in real detail because Japan has one of the oldest and most meticulous habits of record keeping on the planet. They had been writing down tsunamis, carefully, with dates and descriptions and damage, for centuries by that point. Villages flooded, records were made, officials noted what happened and when. All very thorough, all very Japanese, and all preserved. There was only one problem. Nobody in Japan had felt an earthquake. Now, normally, a tsunami is the obvious consequence of a quake you've just lived through. The ground shakes. You know something has happened. And then the sea does something strange, and you connect the two without needing a degree in geology. But this wave arrived with no local earthquake at all. No shaking, no warning, just the sea, suddenly behaving in a way it had no business behaving, on an otherwise unremarkable day. The Japanese records describe a wave that came, in effect, from nowhere. Seismologists have a wonderfully evocative name for this kind of event. They call it an orphan tsunami, a wave with no parent earthquake anywhere nearby to claim it. For a very long time, that's where the mystery sat. An orphan, unexplained. The answer, when it finally came together, was extraordinary, and it came from the other side of the ocean entirely. Off the coast of the Pacific northwest of North America, running for hundreds of kilometers from Northern California up to British Columbia, there's a subduction zone called Cascadia. It's the same sort of beast we've been discussing, one plate diving under another, capable of producing a megathrust giant. And for years, geologists looking at the forests and coastlines of that region kept finding odd things. Whole stands of dead trees, drowned where they stood, the so-called ghost forests, killed when the land suddenly dropped and let the sea rush in. Layers of ocean sand sitting inexplicably inland, dumped there by a wave. Buried soils that spoke of a coastline that had abruptly sunk. All the physical evidence pointed to an enormous earthquake having struck Cascadia, and the science of reading these clues even has a lovely name. It's called paleoseismology, which is essentially geological detective work, the study of earthquakes that happened long before anyone was measuring them, written into the land itself. The trouble was, the land could tell them roughly when, but not exactly when. Tree rings and sediment layers could narrow it down to around the year 1700, give or take, but not to a date, not to a day. And this is where the two halves of the puzzle, an ocean apart, snap together, and I get a small thrill every time I think about it. The Cascadia earthquake had thrown a tsunami westward across the open Pacific. That wave had travelled for the better part of 10 hours, all the way to Japan, where it arrived with no local quake attached and got dutifully written down as an orphan. So the very records that had described an inexplicable wave turned out to be the missing timestamp for an earthquake on the opposite coast. Because the Japanese had logged the wave's arrival so precisely, scientists could work backwards, accounting for how long a tsunami takes to cross the Pacific, and arrive at an astonishingly exact moment for an earthquake that struck a continent away 3 centuries ago, with no instruments and no witnesses who understood what they were seeing. The 26th of January, 1700, at around 9 o'clock in the evening, Pacific time. I genuinely love that. A date and a time, down to the evening, for a prehistoric feeling event, reconstructed from drowned trees on one shore and careful handwriting on another. Two cultures who had never heard of each other, separated by the entire width of the largest ocean on Earth, unknowingly collaborated across 300 years to solve a single mystery. The North American forests held the where and the how big. The Japanese records held the exactly when. Neither was any use without the other. Put them together and you get one of the most satisfying pieces of scientific reconstruction I know of. It also tells you something rather humbling about time, which suits the late hour. The Cascadia zone produces these giants only every few hundred years. From a human point of view, that feels like never, but from the ground's point of view, 300 years is barely a pause for breath. The fault has simply been doing, since 1700, exactly what it was doing before. Sitting locked, gathering strain, holding that swollen door shut. Whatever happens there next is just the same story continuing, on a time scale that makes our worries about next week look very small indeed. And there's a gentle lesson tucked inside the orphan wave, one I'll come back to right at the end. We didn't know that earthquake had happened until we read the land carefully and matched it against someone else's diary. The planet keeps its records whether or not we're paying attention. The trees remembered. The buried sand remembered. The ground holds a far longer memory than we do, And a great deal of modern earthquake science is, in the end, just learning to read what was written down long before us. Right, that's the detective story. Let's stay with water for a bit, because I've mentioned tsunamis several times now, and rather taken for granted that you know how they work. They're stranger than you'd think, and the way we watch for them across the whole Pacific is genuinely one of the better things humans have built together. The word tidal wave needs to be quietly retired, and I'll tell you why. Because it's the root of nearly everything people get wrong about these waves. A tsunami has absolutely nothing to do with the tides. The tides are about the moon. A tsunami is about the seabed suddenly moving. They're completely unrelated, and the old name has led generations of people to picture the wrong thing entirely. The Japanese word tsunami, which translates roughly as harbour wave, won out for good reason, and we should let the tidal business go. So here's what actually happens. When a fault ruptures under the ocean and shifts the seabed up or down, as we touched on earlier, it shoves the entire column of water above it. Not just the surface, the whole depth from the seabed to the top, all at once. And this is the first thing that makes a tsunami so unlike an ordinary wave. The waves you see at the beach are a surface phenomenon, made by wind ruffling the top of the water, just a skin of movement over a still depth. A tsunami is the whole ocean moving. It's a wave that goes all the way down, out in the deep open ocean, that has a strange and slightly unnerving consequence. A tsunami there is barely noticeable. The energy is spread through such an immense depth of water that the wave at the surface might only be a foot or two high, a long low swell that a ship could pass straight over without anyone aboard registering a thing. This is why they used to be so deadly. Out at sea, there's often nothing to see. The danger is effectively invisible until it isn't. And it's moving fast. In deep water, a tsunami can travel at something like the speed of a passenger jet, hundreds of kilometers an hour, racing across the ocean as that low, wide, almost flat swell, which is exactly how the Chilean wave we discussed could cross to Hawaii and Japan in a matter of hours, and how the Cascadia wave reached Japan overnight. They're genuinely quick. The terror only arrives at the coast, and the reason is a bit of physics that's actually quite elegant once you see it. As the wave races into shallower water near land, the bottom of it starts to drag against the rising seabed and slow down. But the water behind is still coming in fast. So all that energy, all that height that had been spread thin and low across deep water has nowhere to go but up. The wave rears, stacks up on itself, and piles into a wall. It's the same volume of water, the same energy, simply forced to stand tall because the shallow ground has run out of room to let it lie flat. A tsunami doesn't grow on its way in, it concentrates. This is also why a tsunami isn't really a single wave at all, and why so many people have historically been caught out. It tends to come as a series, a train of surges, sometimes with the largest one not arriving first. There are grim, recurring stories from before these waves were properly understood, of people walking out onto a suddenly drained seabed after the first surge had pulled the water back, curious, picking up stranded fish, only for the next and bigger wall to arrive. The drawback of the sea before a tsunami is one of nature's few genuinely reliable warning signs, and it's a sign to run inland and uphill immediately, not to go and have a look. Now, against all of that, here's the cheering part, and it's the bit that was working quietly behind the scenes on the 8th of June. Because tsunamis travel fast but the ocean is enormous, there's often a window, a gap between the earthquake and the wave's arrival at distant shores, sometimes minutes, sometimes hours. And humans, to our considerable credit, have built a system to make use of that window. Across the Pacific, there's a network of seismic sensors that detect the earthquake within moments, and ocean buoys and pressure sensors on the seafloor that can actually feel a tsunami passing over them in the open water and report back. Feed all that into a warning centre, and you can raise the alarm for a coastline hours before the wave gets there. That's what happened in June. The quake was detected, The warning went out across the threatened provinces, people moved, and then, crucially, the sensors and the data showed that the waves were small and the threat had passed. The all clear came a few hours later, and everyone could come back down. I keep returning to this because I think it's genuinely underappreciated. Building a system that can shout a warning is impressive. Building one trusted and precise enough that it can also confidently say, actually, it's fine now, you can go home, is in some ways the harder and more valuable trick. A warning system that cried wolf every time and never stood itself down would soon be ignored. The cancellation is part of the design. The whole Pacific-wide arrangement, with countries on every arm of the ring sharing data so that a quake off one coast becomes a timely warning on another, is one of those bits of international machinery that just hums along in the background, saving lives nobody will ever be able to count, because you can't tally the disasters that didn't happen. I find that a rather nice thing to think about as you're drifting off. Somewhere right now, sensors are sitting on the dark Pacific seabed, patiently feeling for a wave that probably won't come tonight, ready to pass the message along the ring if it does. Let's turn next to those magnitude numbers I keep dangling in front of you, and then refusing to explain. It's time. Because what June's quake actually means, set against one of the true giants, is not at all what the numbers suggest at a glance, and it's one of the more counterintuitive things in all of this. Right, the magnitude scale. I've been promising this one all night and quietly enjoying making you wait. Here's the trap that nearly everyone falls into, and it's an honest mistake. When you hear that one earthquake was a magnitude 7 and another was a magnitude 8, your brain does the natural thing and assumes the 8 is a bit bigger, maybe by a 7th or so, one notch up on a scale that runs to 10, you think, so a modest step. That feels reasonable. It is also completely wrong, and the truth is far stranger. The magnitude scale isn't what mathematicians call linear, it's logarithmic, and what that means in plain terms is that each whole number up the scale represents a 10-fold jump in the size of the seismic waves the quake produces. So a magnitude 8 doesn't produce slightly bigger waves than a magnitude 7. It produces 10 times bigger waves, and a magnitude 9 produces 10 times bigger again, which is 100 times the wave size of that magnitude 7. The steps look small written down. They are colossal in reality, but it gets even more dramatic than that, because the wave size isn't the same as the energy released. And the energy is what really matters when we're talking about the destructive power of the thing. When you account for actual energy, each step up the scale represents something closer to a 32-fold increase. Roughly 32 times more energy for each whole number, which means going up 2 whole numbers from a 7 to a 9 isn't 32 times the energy. It's 32 times 32, somewhere around 1,000 times more energy. Let that settle for a second because it genuinely reframes the June quake. The June quake was, by any human measure, an enormous and serious earthquake. And yet, against one of the 9-point-something giants we met earlier, it releases something on the order of 1,000th of the energy. Both of them get described with a single number that starts with a 7, 8, or 9, so they sound like neighbours on a scale. In terms of raw power, they're barely in the same universe. The scale, by compressing these vast differences into tidy little numbers, does a slightly mischievous thing. It makes a 1,000-fold gap look like a couple of decimal points. So what decides where a quake lands on this scale? Mostly it comes down to one thing, and we brushed past it earlier when talking about the giants. It's the size of the patch of rock that breaks. The bigger the area of fault that ruptures in a single event, the more energy comes out, and the higher the magnitude. This is why the truly monstrous quakes are always megathrusts on subduction zones, and it's worth seeing the figures to feel it. The 1960 Chilean earthquake, the largest ever recorded, ruptured something like 1,000 kilometers of the plate boundary in one go. 1,000 kilometers. Picture a tear in the earth running the length of a small country, all letting go at once. That's what a 9.5 takes. This also neatly explains a limit that surprises people. The very largest earthquakes only ever happen on subduction zones, and almost never on the other types of fault. The faults where plates simply slide past each other sideways, the famous San Andreas in California being the textbook example, just can't get as big. Their geometry doesn't allow a single rupture to cover anything like the broad sweeping area a subduction zone offers. As a rough rule, those sliding faults top out somewhere around magnitude 8.5. They can still be devastating, especially because they often run right under cities, but they can't produce the absolute giants. For that, you need a subduction zone and its enormous, gently sloping, locked interface. The Pacific, ringed by subduction nearly all the way around, has more of those than anywhere else, which is the last piece clicking into the picture we've been building all night. A quick word on how we even measure any of this, because the instruments are wonderful. The basic device is the seismograph, and the original principle behind it is almost comically simple. You want to record the ground moving, but your recording pen is attached to the ground, so it moves too, which would seem to defeat the purpose entirely. The clever trick is to hang a heavy weight, so that, thanks to its own inertia, it tends to stay still, even while everything around it shakes. The ground and the frame jiggle, the suspended weight stays roughly put, and you record the difference between them. From that difference, that relative wiggle, you can read the passage of the seismic waves. Modern versions are electronic and absurdly sensitive, networked together across the globe, but the heart of it is still that idea of a still point in a shaking world, which is a rather poetic thing for a machine to be built around. There's one more useful distinction, and it's between how big a quake is and how hard it's felt at any given place, which are genuinely two different questions. Magnitude measures the total energy of the event itself, a single fixed number for the whole earthquake. But how strongly you personally feel, it depends on all sorts of things. How far you are from it, how deep it was, what kind of ground you're standing on. Soft, loose soil can shake far more violently than solid bedrock, even at the same distance. So two people can experience the same earthquake completely differently, and both be telling the truth. The magnitude is the quake's own size. The intensity is your local experience of it, worth keeping the two apart in your head. That's the number then, demystified at last. But all this talk of measuring quakes raises a question I find genuinely lovely, and it's worth a section of its own before we move on. If we've got instruments sensitive enough to read all this, what are they hearing the rest of the time, when nothing dramatic is happening at all? The answer, it turns out, is that the planet is never really silent. There's a comforting fiction we all carry around, which is that the ground is still unless something makes it move. A quiet day is a still day, we assume. Nothing happening down there. But it isn't true. And once you know it isn't true, the world feels a little more alive in a way I find rather nice to fall asleep to. The earth is shaking somewhere, all the time. Every single day, thousands upon thousands of earthquakes happen across the planet. The overwhelming majority of them are tiny, far too small for any person to feel, the kind that register only as a faint scribble on an instrument somewhere. But they're constant. As you lie there right now, the ground beneath some part of the world is slipping, settling, adjusting in countless small increments. The big ones that make the news are simply the rare loud moments in what is otherwise a ceaseless, gentle murmur of motion. The planet doesn't really do stillness, it does quiet, and we listen to all of it. There's a network of seismographs spread right across the globe, in nearly every country, on every continent, even on the deep ocean floor and out on remote islands, all of them quietly recording the ground around the clock, all of them linked together. When a quake happens anywhere on Earth, of any real size, it isn't recorded in just one place. It's picked up by stations all over the world, because the seismic waves spread outward through the body of the planet and arrive, a little later, on the far side. We talked earlier about how the basic instrument works, so I won't go back over that. But the clever part at the global scale is what you can do with many of them at once. Because the waves travel at known speeds, and because they reach different stations at slightly different times, you can work backwards from those tiny differences in timing to pinpoint exactly where and how deep the quake was, often within minutes of it happening, from thousands of miles away. A quake off the Philippines is logged in Europe and the Americas almost immediately, its location triangulated from the gaps between when each distant station first felt the waves arrive. The whole planet, in effect, is wired up as one enormous listening device, and the listening never stops. Now here's the detail that genuinely delights me. Even when there are no earthquakes worth the name, the instruments don't fall silent. They pick up a faint, constant, low background hum, a perpetual gentle buzz in the rock. And for a long time, nobody was quite sure what it was. The answer when it came was wonderful. A great deal of that background hum is the ocean, the endless pounding of waves against the world's coastlines, and the collision of ocean swells far out at sea, drums against the seabed and the shore so persistently that it sets the entire planet faintly ringing, a soft seismic murmur that never stops because the sea never stops. So the ground is humming, right now, with the sound of the ocean leaning on it. The planet has a heartbeat of a sort, and it's made of waves. I think that's one of the loveliest facts I know, and it's a particularly good one to drift off to. There's a grander version of the same idea, reserved for the very largest earthquakes, and it's stranger still. When one of the true giants ruptures, it doesn't just send waves racing across the surface and through the interior, it sets the entire planet vibrating as a single whole, ringing like an enormous bell that's just been struck. The whole Earth flexes and rebounds very slightly in slow, deep oscillations that can carry on for hours and even days after the quake itself has finished. These are tones far, far below anything a human ear could ever hear. Vibrations of the planet as one object, so deep and so slow that a single note might take many minutes to complete. After the largest quakes of recent decades, instruments around the world recorded the Earth, quite literally ringing, the whole globe resonating like a struck bell, the sound fading out over the following days as the planet gradually settled back to its quiet hum. The world, briefly, becomes a musical instrument, playing a note nobody can hear, in memory of an earthquake that's already over. I keep turning that image over because it's so at odds with how we usually think about these events. We frame earthquakes as destruction, as breakage, as the ground failing. And of course they can be that. But there's this other dimension to them, where the same event that brings down a building also sets the entire planet singing a note too low for any ear, a note that lingers for days. The Earth absorbs the shock and rings with it, the way a bell rings, the way a wineglass rings if you flick it. There's something almost dignified in that, the planet taking even its most violent moments and turning them for a while into a long, deep tone resonating through itself. And all of this is being recorded every second, whether or not anyone is watching the readouts in real time. The instruments don't sleep. The ocean keeps drumming its background hum into the rock. The tiny quakes keep flickering across the seismographs. Thousands a day, a constant gentle static of small movements. Somewhere right now, a needle or a sensor is tracing the faint, ceaseless restlessness of a living planet. The same way it did last night and will tomorrow night, patient and unsleeping. You don't have to listen. The instruments are doing it for you. That's rather the point of them. I find genuine comfort in that, more than I expected to when I first learned about it. The idea that the ground is always murmuring, always being listened to, that the planet is never fully still and never fully unwatched. It reframes the quiet of a normal night. It isn't the silence of a dead, fixed thing. It's the quiet of something alive and moving and humming gently to itself, with a whole network of patient instruments keeping it company in the dark. The world is talking to itself very softly, all night long. You can sleep right through it. It'll still be murmuring when you wake. Now, with all that listening in mind, let's go back to something I raised right at the start, the question of whether a quake might be followed by a bigger one, and the gentle, reassuring mathematics of aftershocks. Let me introduce you to a small family of words that the news tends to throw around without ever quite defining, and which, once you understand them, take a lot of the dread out of the days after a big quake. When a large earthquake happens, it is almost never a single isolated event. It comes as part of a sequence, a little cluster of related quakes around it in time. The biggest one in the cluster is called the main shock. The smaller ones that follow it are aftershocks, and the smaller ones that come before it, if there are any, are foreshocks. Simple enough so far, but here's the genuinely interesting wrinkle, the one that makes seismologists careful with their language. You can't actually tell in the moment whether a given quake is a foreshock or a main shock. That label only gets handed out in hindsight. If a quake happens and then a bigger one follows, the first one is retrospectively crowned a foreshock. But if nothing bigger follows, then that first quake was the main shock all along. At the time it strikes, it's wearing no badge at all. It's just an earthquake, and only the future decides what to call it. The textbook example, and the one that always makes the point land, comes from Japan in 2011. 2 days before the enormous Tohoku earthquake we discussed earlier, there was a sizable quake offshore, a magnitude 7.3, which is itself a major event. At the time, naturally, it was treated as the main shock, because that's what it appeared to be. Then 2 days later, the vastly larger 9.0 struck, and in that instant, the 7.3 was demoted in the record books to a foreshock. It hadn't changed. The label had. That's the slippery nature of these things, and it's exactly why nobody can point at a fresh quake and tell you for certain whether something worse is on its way. The category only exists after the fact. Now, this might sound like it ought to be alarming, the idea that any quake could secretly be a foreshock to something bigger. So let me give you the number that puts it in proportion, because it's the most reassuring statistic in this whole field. Around the world, the chance that an earthquake will be followed by a larger one nearby within the following week is roughly 5%, 5 in 100, which means flipped around, that about 95 times out of 100, the quake you've just felt was the worst of it, and everything that follows will be smaller. The odds are heavily, overwhelmingly, that the big one has already happened, not that it's still coming. That single figure is, I think, the quiet antidote to a great deal of the fear that follows a disaster. And the aftershocks themselves, the smaller quakes that do follow, behave with a kindness that's almost mathematical. They fade. There's a well-established pattern, observed again and again across more than a century of records, where aftershocks decrease in both number and size as time goes on. The day after a big quake, you get a lot of them, and some can be strong enough to bring down structures already weakened by the main shock, which is a real danger, and the reason rescue workers stay so alert in those first hours. But as the days pass, they thin out. The week after is quieter than the day after. The month after is quieter still. The energy is settling, the fault is finding its new resting position, and the ground is, in its way, calming down. This is why, when Pivolks said after the June quake that aftershocks could be expected for days and even weeks, that wasn't a threat. It was a description of a fading, a process winding down rather than building up. I think there's something genuinely lovely in that decay, and it's not a sentiment you often get to apply to earthquakes. So much of what we've talked about tonight is about energy building silently, strain gathering, the slow-stuck patience of a locked fault. But the aftermath runs the other way. After the release, the system spends itself out, settling, each tremor a little smaller than the last, the whole sequence trailing off towards quiet. The ground gathers tension over centuries and then lets it go over weeks. There's a rhythm to it. Build slow, release fast, settle gently. Because the pattern is so reliable, it can actually be turned into a forecast, and a useful one. After any significant quake, scientists can estimate, with real numbers attached, how many aftershocks of various sizes to expect over the coming day, week and month, and how likely a larger event is. Those forecasts go straight to the people who need them. The emergency teams deciding when a damaged building is safe to enter, when it's sensible to send rescuers in, when residents can return. It's not guesswork. It's the decay pattern, measured and applied, turning a frightening unknown into a managed risk with odds you can actually plan around. Which brings us at last to the heart of the whole matter, and to that line in the title I promised we'd settle honestly. The difference between forecasting an earthquake and predicting one. Because those two words sound like synonyms, and they are absolutely not. And the gap between them is the gap between real science and the bloke on the internet who claims he knew it was coming. There's an old line about a stopped clock being right twice a day, and it's the single most useful thing to keep in mind whenever someone tells you they predicted an earthquake. I'll come back to the clock. First, the distinction that the whole thing hangs on, because once you've got it, you can never be fooled again. To predict an earthquake, in the way the word is properly meant, would be to say something like this. A quake of roughly this size will strike this specific place within this specific, narrow window of time. A date, near enough. A location, a magnitude. That's a prediction, and it's the thing people imagine science is either secretly capable of or on the verge of cracking. It is not. And I want to be really plain about this because there's a lot of nonsense out there. No scientist has ever predicted a major earthquake in that sense. Not once. The world's geological surveys are completely candid about it. They cannot do it, they don't know how to do it, and they don't expect to be able to do it any time in the foreseeable future. This isn't a funding problem or a technology problem that's about to be solved next year. It comes straight back to that locked silent fault we talked about near the beginning. Right up to the instant it ruptures, a stuck fault gives off no reliable signal that the break is about to happen. Scientists have searched, exhaustively, for decades. For some telltale sign, some precursor. They haven't found one that works. The quake, as far as anyone can presently tell, is genuinely unannounced. Forecasting is an entirely different animal, and this is where the real, impressive science lives. A forecast doesn't name a day. It deals in probabilities and long stretches of time, much more like a weather forecast than a prophecy. A meteorologist on a sunny Monday can tell you there's a 60% chance of rain at the weekend. They can't tell you it'll start at 3:20 on Saturday. That's the spirit of an earthquake forecast too. Scientists can say, with real confidence, that a particular fault is storing up strain, that it has produced large quakes on a certain rough cycle in the past, and that the probability of a major event there over the next few decades is high. What they can't do is circle a date, and they have remarkable tools for the forecasting. They can measure the movement of the plates with GPS precise to the millimetre, watching the strain accumulate in something close to real time. They can read the geological record, the paleoseismology we met in the orphan wave story, to work out how often a given fault has let go across the centuries. Put all that together, and you can identify with genuine authority the places where conditions are ripe, where a fault is loaded and overdue for release in the long-run sense. That's real knowledge, and it saves lives because it tells you where to build strong and where to prepare. It just isn't, and never claims to be, a calendar. So now, the stopped clock. Every time there's a major earthquake, and I mean nearly every single time, somebody surfaces who claims to have called it. Usually, they posted something vague online a few days or weeks before, a warning that a big quake would strike somewhere or soon, often pointing at a region that has earthquakes constantly anyway. When one duly arrives, as one eventually will, they wave their old post around as proof of their gift. There was a particularly famous case after the dreadful 2023 earthquake on the Turkey and Syria border, when a man's earlier social media warning went viral, seen by millions, hailed as a prediction come true. The trouble is, this is the stopped clock, exactly. If you make enough vague, scattershot warnings pointed at the world's most seismically active regions, Some of them are bound to land near a real quake eventually, purely by chance, the same way a clock that stopped will show the correct time twice every day without keeping any time at all. The seismologists' phrase for it is blunt and fair. Scattershot statements. Make enough of them and the law of averages does the rest. The people making these claims aren't, for the most part, sinister, but they aren't predicting anything either. They're playing the odds and showing you the winners while quietly forgetting the thousands of misses. Which brings us, finally and honestly, to the line in the title, is the worst still to come? And here's my genuine answer, the one I've been walking you towards all night, and I think it's a far more interesting answer than the scary version. Yes, but not in the way a prophet would mean it, and not in a way that should cost you a single minute of sleep tonight. On the active fault zones of the world, including the Great Ring around the Pacific, more large earthquakes are not a possibility. They're a certainty. The plates are still moving. The strain is still gathering. The faults that produced the giants of the past are, in many cases, quietly loading up for the giants of the future. So somewhere on the ring, over the coming decades and centuries, more big ones will absolutely come. That is as close to a sure thing as geology offers. In that sense, yes, the worst is always still to come, because the planet is not finished and never will be. But notice what that statement is and isn't. It's a forecast, not a prediction. It tells you the what and roughly the where and absolutely nothing about the when. It's the same kind of certainty as knowing the tide will come back in, or that it'll rain again in a place that gets rain. A certainty so spread out across time that it carries no alarm with it at all. The worst is coming the way next winter is coming. Which is to say, of course it is, and there's not the faintest reason to lie awake over it tonight. And there's a reason you can afford not to, beyond just the long odds, which I want to spend a moment on, because it's the most human part of this whole story, and it tends to go completely unmentioned. Everything we've talked about tonight, the sensors and the networks and the warnings and the forecasts, none of it runs itself. Behind all of that quiet machinery, there are people sitting in rooms, often through the small hours, watching screens so that the rest of us don't have to. And I think they deserve a section because they are, in a literal sense, keeping watch while you fall asleep. At the monitoring agencies around the Pacific Rim, including the one in the Philippines that handled the June quake, there is always somebody on duty. Always. It isn't a 9-to-5 sort of job, because the ground keeps no office hours, and an earthquake is just as likely to arrive at 3 in the morning as 3 in the afternoon. So somewhere, right now, there's a person on a night shift, a mug of something going cold beside them, watching the gentle scribble of the instruments, ready to act the moment that scribble turns into something serious. Most of their nights are utterly uneventful, which is exactly how everyone wants them to be. They are paid in a sense to be bored, and to stay sharp through the boredom, so that on the rare night when it matters, they're awake and ready. There's something I find genuinely moving about that arrangement, the more I sit with it. The whole point of these people is to absorb the worry on everyone else's behalf. You get to go to bed and not think about the fault offshore, precisely because someone whose job it is to think about it is doing so for you. The vigilance is pooled. Rather than millions of people, each lying awake straining to sense the ground, a small number of trained people watch the instruments on behalf of all of them, and the rest are freed to sleep. It's one of the quieter bargains of civilization, and a very good one. And it doesn't stop at borders, which is the part I like best. Because the Pacific is so vast and spans so many time zones, the watching naturally hands itself around the world like a relay. As night falls and the monitoring staff in one country settle in for their shift, it's broad daylight at an agency on the far side of the ocean, fully staffed and alert. The planet's restless edge is never all asleep at once, and neither are its watchers. The duty passes around the ring with the sun, one set of tired eyes handing off to a fresh set somewhere else. around and around without a gap. There is no hour of any day when nobody is watching the Pacific. That coverage has been quietly maintained for decades now, an unbroken human vigil wrapped right around the largest ocean on Earth. I think about the individual people sometimes, the specific person who happened to be on shift on the morning of the 8th of June, who saw the instruments jump and had to move quickly and calmly through a procedure they'd rehearsed 100 times for a moment they hoped would never come. The decision to issue the warning. The hours of watching the sea level data trickle in, hoping it would stay low. And then finally, the quieter decision that the threat had passed and the warning could be lifted, sending everyone home. That's a real person having a genuinely demanding day at work, so that thousands of strangers could be told first to move, and then, with relief, that it was safe to come back. We never learn their names. They wouldn't expect us to. But they were there. It's easy when you read about disasters to picture only the chaos and the damage, the collapsed buildings and the frightened crowds. Those are real, and I don't want to wave them away. But there's this whole parallel layer of calm, competent people doing careful work in quiet rooms, and they're just as much a part of the story, arguably the better part. For every image of destruction, there's an unphotographed person at a desk doing exactly the right thing in the right order. And the reason so many earthquakes pass with far less harm than they might is, in large part, down to them. So when I say there's no reason to lie awake tonight, this is a chunk of what I mean. It isn't only that the odds are in your favour, though they are. It's that you've got people on it, trained, awake, networked across the whole ocean, handing the watch around the world as it turns. You can let the worry go, genuinely, because it's already being held by someone whose job it is to hold it, and who's better placed to hold it than you are anyway. That's not a thing you have to do yourself. It's covered. Which is the perfect note to turn, finally, to the rest of how we cope. The bigger picture of how whole societies have learned to live on ground that won't sit still. Because the watchers are the sharp end of something much broader and rather hopeful. If you can't predict the day, and you know for certain the big ones will keep coming, then the only sensible response is to get very, very good at being ready. And this is the part of the story I find genuinely hopeful, because it's where humans stop being passive and start being clever. We can't stop the ground moving. But over the past century or so, the people of the Pacific Rim have got remarkably skilled at living with a flaw that won't sit still. Start with the few seconds before the shaking. You'll remember we said a quake gives off no warning before it ruptures. That's true. But once it has ruptured, once the break has begun, it sends out seismic waves. And here's the trick. Those waves travel fast, but not instantly. And crucially, the first, gentler waves outrun the later, more destructive ones. And both outrun the news travelling down a wire or through the air. Which means if a sensor near the epicenter detects the very start of a quake, it can fire off an electronic alert that races ahead of the damaging shaking to places further away. Not much of a head start, anywhere from a few seconds to, at best, over a minute. But a few seconds is astonishing when you think about what can be done with it. These early warning systems exist now, and they work. One of the best-known runs along the western coast of the United States, covering California, Oregon, and Washington, sending alerts to people's phones, and just as importantly, to machines. In that handful of seconds, a warning can tell trains to brake before the track starts moving. Halt delicate machinery, open lift doors at the nearest floor so nobody gets trapped, stop surgeons mid-procedure, and shut valves on gas and water lines. A person, woken by an alert, has just enough time to get under a sturdy table, which during a serious quake is very often the difference that matters. It's not prediction. The quake has already begun, but it's borrowing time from the speed of electronics, and it's saving lives with it. When the shaking does arrive, the advice across the whole Pacific Rim has settled, after a great deal of study, on something refreshingly simple. Drop, cover, hold on. Get down low before the quake knocks you down. Get under something solid if you can. or at least protect your head and neck. And hold on to whatever shelter you've got until the shaking stops. It's not glamorous, and it doesn't make for dramatic films, where people always seem to sprint through collapsing doorways. But the unglamorous version is the one that works. Most injuries in earthquakes come from falling objects, and people trying to move while the ground is heaving, not from buildings pancaking. Staying put, low and covered, is overwhelmingly the right instinct, however much it goes against the urge to run. But the deepest protection of all isn't in the moment at all. It's built into the buildings years beforehand, and this is where I think human cleverness really shines. A well-engineered, modern structure in an earthquake zone is a quietly miraculous thing. It's designed to flex rather than snap, to sway with the shaking and absorb the energy instead of fighting it rigidly and losing. The grim truth that seismologists often repeat is that earthquakes don't really kill people. Collapsing buildings kill people, which means the single most effective life-saving measure against an earthquake is, of all the unglamorous things, a good building code, properly enforced. Chile is the example I always reach for here, because it's such a clean demonstration. After the catastrophic 1960 quake, the country took the lesson to heart and steadily strengthened how it built. So when an enormous quake struck Chile again, decades later, in 2010, a genuine monster of an event, the death toll, while still a tragedy, was strikingly low for a quake of that power. The buildings, by and large, held. The codes written in the memory of the earlier disaster did their job half a century on. That's the long game of living on the ring. You pay the price of one disaster in stricter rules, and you collect the dividend in all the deaths that quietly never happen the next time. And the Philippines, where we began tonight, sits squarely inside this world of preparation. The country runs a substantial monitoring backbone, a network of 128 seismic stations spread across the islands, watching the ground constantly, feeding data to the people whose job it is to issue the warnings and the forecasts. That's why, on the 8th of June, the response was so quick and so practiced. The detection, the tsunami warning, the careful all clear a few hours later, none of that was luck. It was the product of a country that has long understood what it sits on and has built the institutions to match. What I take from all of this, and what I gently leave with you as the lamps go down, is that the story of humans on the ring of fire is not really a story of victims. It's a story of adaptation. People have looked at the most restless ground on the planet, decided to stay, because it's also some of the most beautiful and fertile ground on the planet, and then got methodically, generation by generation, better at surviving it. Sensors on the seabed, warnings that outrun the waves, buildings that bend, children who practice drop, cover, hold on at school the way other children practice fire drills. It's one of the better things about us, honestly. We can't argue with the plates, so instead we learn their habits and quietly build our lives to fit around them. Before we wind down for the night, I want to take one last gentle detour into the older, stranger, more human side of all this. The stories people told about earthquakes before we understood them. Because for most of history, we had no plates and no faults, and no GPS, and we still had to explain why the ground would sometimes move. And the explanations people reached for are, in their way, lovely. Long before anyone knew about tectonic plates, people still felt the ground move, and they still needed a reason for it. And I have a lot of affection for the reasons they came up with, because they tell you as much about us as they do about the Earth. When you can't see the cause, you reach for the most powerful image you have. And across the world, again and again, people reached for the idea of something enormous, alive and restless, held beneath their feet. In Japan, the old story had it that a giant catfish lived in the mud beneath the islands, and when it thrashed, the land shook above. A god was meant to keep it pinned down with a great stone, and earthquakes were the moments the god's attention slipped and the catfish managed a wriggle. I find that genuinely charming, and not a million miles off in its way from the truth. They sensed correctly that the cause was something vast hidden underground, mostly still, but occasionally moving. They just dressed it as a fish rather than a fault. The instinct was right, even if the biology wasn't. Other cultures landed on similar shapes, a great creature shifting its weight, a giant turning over in sleep, something colossal carrying the world and occasionally adjusting its grip. Across places that had no contact with each other, the human mind kept arriving at the same basic notion that the ground we trust is resting on something enormous and not entirely tame, which, if you squint, is more or less what the science eventually confirmed. We do live on top of something vast and slowly moving. It just turned out to be rock rather than a beast. While we're on folklore, I should address the animals, because it comes up every single time, and people have strong feelings about it. The claim is that animals can sense earthquakes coming, that dogs get restless, birds go quiet, that sort of thing, and that we do well to watch them. And honestly, I want it to be true, because it's a wonderful idea. The careful answer is that there are loads of anecdotes and very little solid repeatable evidence. It's entirely plausible that some animals pick up on the faint, fast early waves of a quake a moment or two before the heavy shaking. The same first waves our warning systems detect, which would explain a dog reacting a few seconds early. That's not really precognition though. That's just better hearing of the start of the same event. The grander claim that animals know hours or days in advance has never stood up to proper scrutiny, and given that, as we've covered, the fault itself gives off no reliable warning signal, it would be a bit strange if your cat could detect something the world's most sensitive instruments can't. So, lovely idea, weak evidence. I'd file it under wouldn't it be nice rather than set your alarm by the budgie. Here's a small fact I think is quietly profound, and it suits the late hour. Coastlines, remember. We touched on this with the ghost forests and the buried sands back in the Orphan Wave story. The land itself keeps a record of the great quakes, written in drowned trees and layers of sediment and raised or sunken shores, a record that can be read centuries later by anyone who learns the language of it. The ground has a far longer memory than we do. A human community might forget a disaster within 3 or 4 generations. The survivors gone, the stories worn thin. But the sediment doesn't forget. The dead trees stand there for hundreds of years, patiently holding the date. There's something almost tender in that. The planet keeping the records we're too short-lived to keep ourselves. And this is where the old stories and the new science quietly shake hands, which I rather love. The Japanese kept written records of waves for centuries out of sheer diligence, and those records ended up solving a scientific mystery on the far side of the ocean 300 years on. The folklore impulse to mark the strange event, to write it down, to tell the story so it isn't lost, turned out to be doing real geological work without knowing it. The catfish and the seismograph are, in the end, part of the same human project. Both are us trying to make sense of the restless ground, to hold on to what it does, to turn something frightening into something understood. We've just got better instruments now. The impulse hasn't changed at all. I think that's the note I want to carry into the last few minutes. For as long as there have been people on the Pacific Rim, there have been people telling stories about why the ground moves, marking the events, passing the knowledge down. The methods have come an extraordinarily long way, from giant catfish to seafloor sensors. But the thing underneath it, the wish to understand the world we stand on, rather than simply fear it, runs unbroken all the way back. That feels like a good thing to be part of. A very long, very patient conversation between people and the ground they live on. Let's bring it gently home. Let's go back, one last time, to that Monday morning, the first day of school. The uniforms a size too big, the shuffle of bags and shoes, all of it utterly ordinary, right up until 37 minutes past 7, when the ground in southern Mindanao decided to let go of something it had been holding for a very long time. It looks different now, doesn't it, that morning, than it did when we started. At the beginning of the night, it was a frightening headline. A magnitude 7.8 out of nowhere, A tsunami warning, the worst supposedly still to come. And now, having spent a couple of hours together, you can see all the machinery behind it. A locked fault, finally slipping. A patch of seabed shoved upward, nudging the water above into a modest wave. A warning system that did exactly what it was built to do, raised the alarm, and then, a few hours later, had the wisdom to stand it down. An aftershock sequence, already fading by the laws of its own gentle decay. And a region that has had this conversation with the ground many times across the generations, and knew, more or less, how to answer. None of it was meaningless. None of it was a punishment. It was the planet doing the most ordinary thing a living planet does on the most active stretch of crust it has, in a way people there have understood and prepared for far better than the headline ever lets on. And the worst still to come? We sorted that one out, I hope. Yes, more big ones will arrive on the ring, somewhere, across the decades and centuries ahead, because the plates are still moving, and the strain is still gathering, and the faults are still loading, exactly as they have for millions of years. That much is certain. But it's the certainty of next winter, not the certainty of a prophecy. Nobody can tell you the day, and anybody who claims to is reading a stopped clock. The honest forecast is simply that the Earth isn't finished, which is another way of saying the Earth is still alive, which is, when you think about it properly, the whole reason any of us are here to worry about it at all. I keep coming back, as we close, to that wave from 1960, the one that crossed the entire Pacific from Chile and reached among so many other shores the very coast of the Philippines we began on tonight. The whole ocean is connected like that. A rupture on one rim is felt, eventually, on the far one. And I find oddly that the same fact that ought to feel ominous feels almost comforting at this hour. Everyone on that vast ring is on it together, downstream and upstream of one another, sharing the sensors and the warnings, and the hard-won knowledge, the catfish stories, and the building codes alike. It's a strange sort of fellowship, the whole population of the Pacific Edge, but it's a real one. So here's where I'll leave you. The ground will move again, somewhere, someday, the way it always has. And the very same science that can't tell us when is the reason warnings reach phones before the waves reach shore. The reason buildings bend instead of breaking. The reason a region can take a serious blow on a Monday morning and stand its tsunami warning down by the afternoon, not knowing the day turns out to be perfectly survivable, as long as you're ready for any of them. And the people of the ring are getting readier all the time. The strain builds slowly, over lifetimes. The release is quick, and then the ground settles, tremor by smaller tremor, back towards quiet. Build slow, release fast, settle gently. It's not a bad rhythm to fall asleep to, honestly. The whole restless Pacific, doing the only thing it knows how to do, on the long patient timescale of stone. That's more than enough from me. The ground can keep its own watch tonight. And so can the sensors out on the dark seabed, feeling for a wave that almost certainly isn't coming. Rest easy. There'll be more of these another night, if you'd like them. Sleep well.